Okay, so now let's focus on these potential energy graphs, okay, or potential energy curves. This will probably be the most difficult part of this chapter or unit because this is a new topic, especially if you've taken it AP Physics before. Right, again, remember AP Physics C is taking your knowledge from AP Physics 1 and just adding calculus to it, and that's what we do with these potential energy curves. Okay, so a potential energy curve or potential energy, remember, only depends on the position of an object. Okay, remember, all those conservative forces that we talk about or we've spoken about, they have potential energy associated with them. Now, we can graph potential energy as a function of position. Right, and again, this is just going to be potential energy versus position, right? PE versus X, or we use the symbol U for PE. So such graphs are called potential energy curves. And they're going to tell us like a lot of information, right? We can get a lot of things from these potential energy curves just by the graph and understanding what the graph does, all right? Now remember that the derivative of potential energy is force, and more specifically, it's the negative derivative, okay? But the magnitude of that derivative, okay, or the derivative of potential energy is the magnitude of force, right? So at some point in time, you may have to do, right, negative du dx, right? So therefore, the steeper the potential energy, the more force is acting on an object placed at that location, all right? I didn't point it out, but understand that from this information, you could find the equilibrium point as well, right? And so if you remember from calculus, when you set the derivative equal to 0, right, you're finding where the slope is 0, where in this case, you know, if the derivative of potential energy is force, this is where equilibrium occurs, right? So one way to analyze a potential energy graph is just to simply imagine it being a roller coaster, okay? So a ball on a roller coaster that's physically making the track, right? And so what that means is the steeper the graph, right, the more or greater the force, right, or acceleration, right? So the steepness will tell you, you know, essentially, you know, how big or small the force or acceleration is, okay? And remember, the force is always downhill, right? Force always wants to go to lower potential energy, right? And so if, let's just say I have an object, right, traveling on an incline, the force is going to bring it downhill because there's less potential energy down here than there is up to the top, right? So remember, force goes downhill. And then the higher the object is on the potential energy track, the slower it goes, right? Why? Because there's less kinetic energy, right? And so kinetic energy would be less than your potential energy. If there's less kinetic energy, there's less speed, right? And then there's a horizontal line called the total energy line, above which an object cannot go, right? So total, remember, you can't go any higher than the amount of energy that is already in the system, right? If you go above that line, you have to add energy to the system, all right? And so here's an example. This is an object with a mass of 9 kilograms initially at position x equals 0 and is moving to the right. The object is subject to a conservative net force such that the potential energy of the object is given by the function u of x equals 20 over 1 plus x minus 3 squared. And the graph of the function is shown here to the right. And I forgot to do, so this is our potential energy, and this is our position axes, right? And so A, what minimum initial velocity must the object have at x equals 0 in order to make it to x equals 6 meters? Okay. B, describe how the magnitude of the acceleration changes from x equals 3 meters to x equals 6 meters. And then what function represents the amount of force the object experiences with respect to position, and then sketch the position versus time and velocity versus time graphs for the object as it travels from 0 to 6 meters. Okay, so part A, what minimum initial velocity must the object have, right, to start? So again, this graph is just potential energy versus potential energy versus position. But this does tell us that the total amount of energy in the system is 20 joules. Okay, and we know that the total energy is simply kinetic plus potential. All right, and so that has to be greater than 20. That has to be greater than 20 joules, right, to get from 0 to it should be greater than or equal to 20, right? Because up here that means it'd be 0 velocity, which means it would make it, but it may not carry off to the other side, right? And so as we go through, right, we know the kinetic energy formula is 1/2 mv squared. We already know that there's 2 joules of energy already at the beginning, so it's going to be our initial, right, initial energy. And then we just really just do some algebra, right, do some math on the way down. So we're going to have 1/2 times 9 times v squared, because it tells us a 9 kilogram object. And then I'm going to subtract 2, which tells me it's going to be greater than or equal to 18. And then so this becomes 4.5 v squared is greater than or equal to 18. V squared is greater than or equal to 4, which means that my speed has to be greater than or equal to 2 meters per second. Right? So I have to be traveling at least 2 meters per second to carry that energy up to the top here. All right. Now, part B, what we're going to do is we're going to look at the shape of the graph. So describe how the magnitude of the acceleration changes from x equals 3 meters to x equals 6 meters, right? So here's 3 meters, here's 6 meters, right? And so we're looking from here. So what I really do is understand that there's a relationship between acceleration and force, right? They're directly proportional to each other, and that the magnitude of the force, right, is equal to the slope of this graph. And so what we're going to do is simply, where did my pens go? Okay, and so what we're going to do, right, is if we look at the slope of this graph, right, how is this going from here to here to here and to here? And so something you'll see is at 3.5, so from 3 to 3.5, from 3 meters to 3.5 meters, right, you're going to see that it's a steep slope, right? And so that means that the acceleration is increasing. Okay. And then from the rest of the way, if I look at the lines I drew, my slope is starting to decrease, which means that means my force and acceleration are also decreasing. And so from 3.5 to 6 meters, right, the acceleration would decrease. Oh, I'm kind of spelling the word decreasing here. Okay, and so that's what's happening. So you notice that it's kind of like a mixed bag, right? So part of the time the acceleration will increase, part of the time it will actually decrease. And again, we found that by looking at our slopes, right? So from 3 to 3.5, right, my slope is going to be kind of increasing until it reaches a point at 3.5, and then it turns and then it starts to go back to decreasing. Okay, and again, we're looking at the slope. Okay, but remember, the magnitude of the force is the slope, right? But the direction, okay, it's always downhill, right? And so that you have to remember that, right? Part C is the fun part of this problem, right? So it's really going to test our calculus ability here, right? And so I'm just going to write the function down real quick. So u of x equals 20 over 1 plus x minus 3 squared, okay? So the question says, what function would represent the force, right? And so we need to take the derivative of this. So force, remember, is negative derivative of the potential energy function. So basically, we're going to do negative d dx of this function. Okay. Now the function looks scary because it's it's essentially a fraction, but you can do some rewriting here to make this more simple. So I'm going to say that this is going to equal, I'm going to factor out a 20, right? Just so I'm looking at the like 1 over this function. But 1 divided by something is the same thing as just saying to the negative first power. Okay. Use brackets for the outside there. Okay. So now, right now, it looks a little bit, I can do this, right? So this is a chain rule function, or something I use a chain rule with, right? And so remember, chain rule, right? The way I like to say it is derivative of the whole thing, right? And so we say, if we just say u, so u prime, right, times the derivative of the inside. So just remember, derivative of the whole thing, right, and derivative of times the derivative of the inside, right? And so let's do that. Okay. So the derivative of the whole thing, so we got negative 20 times, now derivative would be negative 1, right? And then I have my whole thing, I have my whole function here. Right, so there will remember n minus 1 to the n minus 1. So this is going to be minus 1, right? Now I have to take the derivative of the inside. So now I have to do 1 plus x minus 3 squared. Well, that's pretty easy because derivative of 1 is just 0. Now I have to do a little bit of a chain rule here too, but that's going to actually end up being a simple one because it's going to be 2, right? Derivative of the whole thing. Right, bring down the exponent, subtract 1. And then derivative inside of this one is just 1, right? And so I have to multiply this whole thing by 2 times x minus 3. Okay, so there's my function, but let's rewrite this, right? Because this is a negative 2, which means I can put it in the denominator, right? So this ends up being 1 plus x minus 3. Oh, I forgot a squared. I don't know why I'm bending over. I've got plenty of room to do this, right? So x minus 3 squared, right? So that whole bottom is squared because it's a negative 2. And then I have a negative 20 up top. I have a negative 1 here that makes it positive, but I have a 2 here, so it makes it 40. And then I have this x minus 3. So the force as a function of x, or a position, is simply 40 times x minus 3 over 1 plus x minus 3 squared, and then that squared, right? And so what that function actually looks like, it's a pretty cool function, and it looks something like this. Okay. And so you can, look at this idea that it should match up, right? Based on, if we look at this original graph, what's happening, right? So increase here, right? And then we've got this quick little increase, right? And then we got this decrease. And if you look at our function, right? Increase, right? So increase, and then a quick, right? And then we decrease, and then we get back there, okay? All right. The last part says to sketch the position versus time graph of this function, okay? Let me erase my lines here, just so we can have a clean to look at this, okay? And so the way to think about it is, if I take a marble, what is happening to that marble, right, as we're traveling along this roller coaster? And so from 0 up to 3, something you'll see is that we're kind of, we're decreasing, right? But we're actually moving forward. Okay, then we get up here, then we start to, kind of flatten out, right? And we're getting close to 0, and then we're going to kind of increase on our way down, right? And so what does that look like, right, in a position versus time graph? So we have, position, time, right? And so we're going to negatively accelerate, right? And then essentially we're going to kind of be constant for a little bit or near constant. So negatively accelerate, kind of be constant, and then we're going to positively accelerate, right? And so if you want, like this is x equals 3, or I'm sorry, I'm writing in times, but I don't know the exact times, but I just lost my axis. Okay. Okay, so that would be our position versus time graph, right? And now let's do our velocity versus time graph, right? So we want our velocity versus time graph to kind of match our position versus time, right? And so we're going to start with velocity. We're going to decrease, get really close to 0, and then we're going to go back to increasing, okay? Oh, sorry, I forgot to label these. So that's our velocity versus time graph. And what I'll do is I'll post some more position or potential energy curve graph examples as we kind of work through this, because again, these are probably our more difficult sections or topic here in conservation of energy.